Dr. M. P. Jayaraman is an assistant professor in mathematics in L.N. Government College, Poneri. He has specialized on geometric function theory. With 14 years of teaching experience, he has handled topics on probability and queuing theory, discrete mathematics, random process, and engineering mathematics. Being a recognized supervisor for guiding PhD and MS students of Anna University, he is the reviewer of the journal Computer Mathematics and Applications. He has also written books on discrete mathematics and has also published papers in 28 international publications, in 4 national publications, and has presented papers in 2 international and in 2 national conferences.
Welcome you all for UGC lecture series in mathematics. In this session, our interest is to solve a nonlinear programming problem involving more than one constraints. For that, the idea is consider a nonlinear programming problem, maximize or minimize z equal to f of x subject to the constraint hi of x equal to 0, x is non-negative. Here the number of constraint hi of x equal to 0, I varies from 1 to m. Therefore, it has more than one constraints. The first constraint we name it as h1 of x, where h1 of x is g of x1 etc. xn variable minus c, and h2 of x is the second constraint. h2 of x is g2 of x1 x2 etc. xn minus c. So, in this session we are going to solve a NLPP involving exactly 2 constraints, both the constraints of equality type. To solve such type of nonlinear programming problem, we make use of necessary and sufficient condition for the general nonlinear programming problem. We know very well, in order to obtain the necessary condition to solve a nonlinear programming problem, we need to form a Lagrangian function, which we know very well that the Lagrangian function is L of x comma lambda equal to f of x minus summation I equal to 1 to m lambda I hi of x. Suppose our problem involves 2 constraint, means the corresponding Lagrangian function is f of x minus lambda 1 into h1 of x minus lambda 2 into h2 of x. From this Lagrangian function, these 2 equations dou L by dou x j equal to 0 and dou L by dou lambda equal to 0 gives the necessary condition for a given nonlinear programming problem. Next, we know very well the sufficient condition for solving NLPP defined in terms of bordered Hessian matrix. The stationary point x naught is a maximum point if starting with principal minor of order 2m plus 1 to last n minus m principal minors of HB naught form on alternating sign pattern starting with minus 1 power m plus n. What it means suppose the given NLPP involving 2 variables and it has 2 constraints, that means n value equal to 2 and m value equal to 2, then minus 1 power m plus n is minus 1 power 2 plus 2, which is minus 1 power 4, which is positive. So, the sign of HB naught, the first principal minor, the sign should be plus 1 plus, the next sign is minus, next sign is plus, alternatively the sign comes, the first sign start with minus 1 power m plus 1. This is the condition for maximum point. Then x naught is minimum point if starting with principal minor of order 2m plus 1 to last n minus m principal minors of HB naught have the sign of minus 1 power m. So, x naught is a minimum point if the border Hessian matrix sign is minus 1 power m. Suppose for this problem the number of constraint is 2, then minus 1 power 2 is positive. For such a case, the sign of border Hessian matrix, the determinant value of HB naught should be a positive sign, should be a positive. Now, the first problem is solve the nonlinear programming problem, which is maximizing z equal to 6x1 plus 8x2 minus x1 squared minus x2 squared subject to the constraints 4x1 plus 3x2 equal to 16, and the second constraint is 3x1 plus 5x2 equal to 15, x1 x2 greater than or equal to 0. So, this is a nonlinear programming problem involving two decision variable x1 and x2 and two constraints, both the constraints of equality type. Since the number of decision variable is 2, for this problem our n value is 2. Since this NLPP consisting of two constraints, our m value for this problem is 2. So, for a given NLPP, the n value equal to 2 and m value equal to 2. Now, with the help of necessary condition and sufficient condition, we try to solve this problem. In order to obtain the necessary condition, first we have to form the Lagrangian function. For this problem, the Lagrangian function is 6x1 plus 8x2 minus x1 square minus x2 square. That is the objective function of our given nonlinear programming problem, minus lambda 1 into 4x1 plus 3x2 minus 16, which is the first constraint of the given problem, minus lambda 2 into 3x1 plus 5x2 minus 15, which is the second constraint of the problem. Therefore, the given problem, the Lagrangian function in terms of Lagrangian multipliers lambda 1 and lambda 2 is 6x1 plus 8x2 minus x1 square minus x2 square, minus lambda 1 into 4x1 plus 3x2 minus 16 minus lambda 2 into 3x1 plus 5x2 minus 15. Now, the necessary conditions are dou L by dou x1. For this problem, the partial derivative of this function with respect to x1 is 6 minus 2x1 minus 4 lambda 1 minus 3 lambda 2 equal to 0. The second condition is dou L by dou x2 equal to 0, which implies the partial derivative of this function with respect to x is 8 minus 2x2 minus 3 lambda 1 minus 5 lambda 2 equal to 0. The next condition is dou L by dou lambda 1 equal to 0, which gives us minus of h1 of x equal to 0. Therefore, for this problem, dou L by dou lambda 1 equal to 0 gives us 4x1 plus 3x2 minus 16 with the negative sign equal to 0. The final necessary condition is dou L by dou lambda 2 equal to 0. For this problem, dou L by dou lambda 2 equal to minus of 3x1 plus 5x2 minus 15 equal to 0. So, we name this as equation 1, 2 and 3 and 4. So, the necessary condition dou L by dou xi equal to 0. For this problem, dou L by dou x1, dou L by dou x2 equal to 0 gives the first two equation, and dou L by dou lambda j. For this problem, dou L by dou lambda 1, dou L by dou lambda 2 gives equation 3 and 4. Now, by solving the simultaneous equation 1, 2, 3, 4, we try to get the value of x1, x2, lambda 1, lambda 2, which gives the solution for the given problem. Now, from equation 3, we simplify the equation 3 as 4x1 plus 3x2 equal to 16. Now, from equation 4, we have 3x1 plus 5x2 equal to 15. We name it as equation, this is equation 3, this is equation 4. Now, by multiplying equation 3 by 3, so we multiply equation 3 by the number 3, equation 3 implies 12x1 plus 9x2 equal to 48. Now, by multiplying equation 4 by 4, we have 12x1 plus 20x2 equal to 60. Now, by solving this equation, we can get the value of x1, x2. By subtracting this equation, we have minus 11x2 equal to minus 12. From this, our x2 equal to 12 by 11. So, from equation 3 and 4, by solving those two equations, we got our x2 value as 12 by 11. Now, by substituting this x2 either in 3 or 4, we will get the value of x1. I will make use of equation 4. Substitute x2 value equal 12 by 11 in equation 4. We have 3x1 equal to 15 minus 5 into 12 by 11. So, which gives us 165 minus 60 by 11, which is 105 by 11, which is nothing but 105 by 11. So, our 3x1 equal to 105 by 11. From this, our x1 equal to 105 by 3 into 11, which is nothing but 105 by 3 into 11. So, we can cancel this 3. So, we got x1 value as 35 by 11. So, with the help of this necessary condition, we will get the optimum value is our x0 value is x1 is 35 by 11 and x2 is 12 by 11. So, with the help of necessary condition, we will get the solution for this nonlinear programming problem is 35 by 11 and 12 by 11. X1 takes the value 35 by 11, x2 takes the value 12 by 11. Now, we make use of the sufficient condition. That means, we are interested in finding the bordered Hessian matrix for this given problem. So, in order to form a bordered Hessian matrix, we need the partial derivatives. First, let me find the partial derivatives. The dou L by dou x1, which gives us 6 minus 2 x1 minus 4 lambda 1 minus 3 lambda 2. Then dou L by dou x2 gives us 8 minus 2 x2 minus 3 lambda 1 minus 5 lambda 2. Then dou L by dou lambda 1, which gives us minus of 4 x1 plus 3 x2 minus 6 equal to 0. And dou L by dou lambda 2 gives us minus of 3 x1 plus 5 x2 minus 15 equal to 0. Now, the problem involves two decision variable, therefore, n value equal to 2 and number of constraint is 2, therefore, m value equal to 2. Therefore, the order of the border Hessian matrix is m plus n cross m plus n. Therefore, the border Hessian matrix order is 4 cross 4. M plus n is 2 plus 2 is 4. Our order of border Hessian matrix is HB naught is 4 cross 4. This border Hessian matrix has 4 blocks. The first block is null matrix of order m cross m. Here our m value is 2. Therefore, the first block consisting of a null matrix of order 2 cross 2. Then the second block is u. U is nothing but partial derivative of h with respect to the decision variable. So, the first h1 is this one. Therefore, dou h by dou xn gives us 4. Therefore, first row takes the value 4. Then dou h1 by dou x2, which gives us 3. So, in the second block, the first column is 4 comma 3. Next one is dou h2 x by dou xn dou x2, which gives us dou h by dou x1 is 3. Then dou h2 by dou x is 5. Now, this block is transpose of this matrix. Therefore, this is 4 3 3 5. Now, this block is matrix V. We know very well V is the second order partial derivative of L with respect to the decision variable xi and xj. So, here dou L by dou x1 is there. By differentiating this, once again we will get dou squared L by dou x1 dou x2. So, dou squared L by dou x1 squared is minus 2. Therefore, the first entry is minus 2. Then dou squared L by dou x2 dou x1, since there is no x2, it takes the value 0. Then the second row, dou squared L by dou x2 squared, which we have minus 2, therefore in this place minus 2. So dou squared L by dou x1 dou x2, there is no x1, therefore it takes the term 0. So for the given problem, the order of the border Hessian matrix is 4 cross 4. The first block is 2 cross 2 null matrix. The second one is 2 cross 2. With respect to the constraints, we got this block. This is a transpose of this one, and this block we are getting by making use of the second order partial derivative of L with respect to xi xj. Let us have a break. Before break, we discussed about the necessary and sufficient condition for solving nonlinear programming problem. With the help of the necessary condition, we obtained solution for a problem. Now, for this problem, we obtained the border Hessian matrix. Now, for this problem, our n value is 2, m value also 2. Since n value is 2 and n minus 1 value is 1, for this matrix, in order to get the sufficient condition, it is enough to find the determinant value of the border Hessian matrix HB naught. So, we are interested in finding the determinant value of HB naught. For that, we find the determinant value of HB naught along the first row. So, the first entry 0, second entry 0, the third entry plus 4. So, 4 into, by omitting the corresponding row and corresponding column, by collecting the remaining row and column, we have the matrix 0 0 5, 4 3 0 and 3 5 minus 2. Next, minus 3 into, by omitting this corresponding row and corresponding column, we have 0 0 3, 4 3 minus 2 and 3 5 0. Now, if we find the determinant value of this one, we have 5 into 4 into 5 20, minus 3 into 3 9. So, 11, 11 into 5 55. So, 4 into 55 minus 3 into, now the determinant value of this matrix is, if we take 3, 4 into 5 20, minus 3 into 3 9, 20 minus 9 11. So, 3 into 11 33. So, the determinant value is 220 minus 99, which we have 121. Now, the determinant value of the border Hessian matrix is HB naught, the value is 121, which is greater than 0, positive. Now, for this given problem, minus 1 power m value is minus 1 power 2, which is positive. So, the determinant border Hessian matrix value is coincide with, the sign coincide with minus 1 power m positive. Therefore, this problem gives the minimum value for the given objective function. Problem is, solve the nonlinear programming problem which optimize z equal to 4 x1 squared plus 2 x2 squared plus x3 squared minus 4 x1 x2 subject to the constraints x1 plus x2 plus x3 equal to 15, and the second constraint is 2x1 minus x2 plus 2x3 equal to 20, and all the decision variables are non-negative. So, the given nonlinear programming problem involving 3 decision variable x1, x2, x3 and 2 constraints. Therefore, for the given problem n value is 3 and m value equal to 2. Now, as usual, to find the necessary condition, we need the Lagrangian function. So, for this problem, the Lagrangian function f of x1, x2, x3 minus lambda 1 into h1 of x1, x2, x3 minus lambda 2 into h2 of x1, x2, x3, which gives us L equal to 4x1 squared plus 2x2 squared plus x3 squared minus 4x1, x2 minus lambda 1 into x1 plus x2 plus x3 minus 15 minus lambda 2 into 2x1 minus x2 plus 2x3 minus 20 equal to 0. Now, for this problem, the necessary, to find the necessary condition, we should find dou L by dou x1 equal to 0, which gives us 8x1 minus 4x2 minus lambda 1 minus 2 lambda 2 equal to 0. The next condition, dou L by dou x2 equal to 0 gives us 4x2 minus 4x1 minus lambda 1 minus lambda 2 equal to 0. The third necessary condition is dou L by dou x3 equal to 0, which gives us 2x3 minus lambda 1 minus 2 lambda 2 equal to 0. The fourth condition, dou L by dou lambda 1 equal to 0, which gives us minus of x1 plus x2 plus x3 minus 15 equal to 0. And the final condition, dou L by dou lambda 2 equal to 0, this equation gives us minus of 2x1 minus x2 plus 2x3 minus 20 equal to 0. So, the necessary condition dou L by dou xi I equal to 1 to 3 gives us the first three equation, equation 1, equation 2 and equation 3. The next condition, dou L by dou lambda j equal to 1 to 2 gives us the fourth equation and fifth equation. Now, we have 5 simultaneous equations in our hand, in which x1, x2, x3 are variables, lambda 1, lambda 2 are constant. Now, by solving this simultaneous equation, as we discussed earlier, we can get the solution. So, the solution for this problem is, we will get the x1 value as 33 by 9 and x2 value as 10 by 9 and x3 value as 8. So, by solving this simultaneous equation, we will give the solution as x1 equal to 33 by 9, x2 equal to 10 by 9 and x3 equal to 8. Now, in terms of bordered Hessian matrix, we can verify the sufficient condition. For this problem, the order of the bordered Hessian matrix HB naught is, since n equal to 3, m equal to 2, the order of the bordered Hessian matrix is 5 cross 5. With the help of this equation, now we try to find the bordered Hessian matrix for this problem. So, our bordered Hessian matrix order is 5 cross 5. So, HB naught is this one. Since it is a 2 constraint problem, the first block has 2 cross 2 null matrix, which have 0 0. Now, we have 2 constraints, therefore, the second block matrix is 2 cross 3. So, with the help of this h1 of x, the first row we got it as dou h1 by dou x1 is 1, dou h by dou x2 is 1, dou h by dou x3 equal to 1, therefore, first row is 1. Now, with the help of second constraint, we can get the second row of this block. By differentiating this with respect to x1, x2, x3, we have the second matrix as 2, minus 1 and 2. Now, this is the transpose of this one, therefore, we have 1 1 1, 2, minus 1, 2. Now, the second order partial derivative of dou L by dou x1, dou L by dou x2, dou L by dou x3 gives this matrix, which we have 8, minus 4, 0, and the second column is minus 4, 4 and 0. Then with respect to this equation, we will get the third row, which we have 0, 0, 2. So, from this Lagrangian function, the bordered Hessian matrix for the given problem is this one. Now, for this problem, m value equal to 2, minus 1 power m equal to minus 1 power 2, which is a positive sign. So, in order to verify the sufficient condition, it is enough to find the determinant value of HB naught alone, because n minus 1 value is 1. So, for this problem, if we find the determinant value of HB naught, the value we get is 72, which is positive. Therefore, this problem gives the minimum value. Let me recap. The necessary condition for a nonlinear programming problem involving 2 constraints, both of equality type, is constructing Lagrangian function L of x comma lambda is f of x minus lambda into h I of x. From this Lagrangian function, the equation dou L by dou x j equal to 0 and dou L by dou lambda j equal to 0 gives us the necessary conditions. The sufficient condition is the stationary point x naught is maximum if the principal minor of order 2m plus 1 to the last n minus m principal minors of h b naught form on alternating sign pattern. The first sign will be minus 1 power m plus 1. Then x naught will be a minimum point if the principal minor of order 2m plus 1 to the last n minus 1 principal minors of h b naught have the sign of minus 1 power m. The question is, solve the nonlinear programming problem which minimize z equal to x 1 plus x 2 plus x 1 square plus x 2 square plus x 3 square subject to the constraints x 1 plus x 2 plus 3 x 3 equal to 2, and the second constraint is 5 x 1 plus 2 x 2 plus x 3 equal to 5. The decision variable x 1, x 2, x 3 are greater than 0. The given nonlinear programming problem involving 3 variables, therefore n equal to 3, and 2 constraints, therefore m equal to 2. Now, in order to minimize this objective function, we should make use of the Lagrangian function. For this problem, Lagrangian function is L of x comma lambda is the objective function x 1 squared plus x 2 squared plus x 3 squared minus lambda 1 into h 1 of x, where h 1 of x is x 1 plus x 2 plus 3 x 3 minus 2 minus lambda 2 into the second constraint 5 x 1 plus 2 x 2 plus x 3 minus 5 equal to 0. So, from the given problem, first we will construct the Lagrangian function. Now, with the help of this Lagrangian function, we will find the partial derivative of dou L by dou x I equal to 0, I varies from 1 to 3, and dou L by dou lambda j equal to 0, j varies from 1 to 2, we will get the 5 simultaneous equation. Now, by solving those 5 simultaneous equation, we will get the solution for this problem. Now, in order to verify the sufficient condition, we have to construct the border Hessian matrix. Since this problem involving 3 decision variable and 2 constraint, the order of the border Hessian matrix is m plus n cross m plus n, which is 5 cross 5. Now, in order to check the sign of border Hessian matrix, we have to compute n minus m value. For this problem, n minus m value equal to 1. Therefore, the sufficient condition for this problem is, to find the sufficient condition, it is enough to find the determinant value of h b naught alone, which should have a sign of minus 1 power m minus 1 power 2, which is positive. Thank you.